This video is about initial value problems. I'm going to give you some definitions of initial value problem and initial conditions. We're going to look at some IVPs. That's my abbreviation for that initial value problem in general. And then we are going to solve some simple initial value problems. Okay, so this is the definition. An initial value problem is a problem consisting of a differential equation and what are called initial conditions. And your goal is to find a function that satisfies both the DE and the initial conditions. Since we are in an ordinary differential equations class or an elementary differential equations class, it doesn't feel elementary, we will look at an ordinary differential equation. So let's say we're given this, an nth order ordinary differential equation and n initial conditions, which I will abbreviate by IC. So those are NICs. Now, we'll assume that we can take the differential equation and solve for that highest order derivative in the differential equation. So maybe it looks like this. And let's say our dependent variable is y and our independent variable is x. Of course, those could be different variables. So we've got the nth derivative of y with respect to x equals some function of everything else. So it'd be a function of the independent variable, the dependent variable, and then all of the derivatives except this one. So it might be a function of y prime and y double prime all the way up to the n-1th derivative of y. That's an nth order differential equation. Now, I know this looks very abstract, and it is abstract, but let me give you a concrete example. This function on the right-hand side will be known. It'll be given to you. So let's say we've got a fourth order differential equation, and you're able to solve it for the fourth derivative of y with respect to x. That might be equal to 2 times x cubed minus dy dx plus x times y. Now this function on the right-hand side is this function over here. This is supposed to be a function of x, y, y prime, and all of the other derivatives. This, oops, that should be a 4. This says the nth derivative of y with respect to x is equal to this. It's a function of x, it's a function of y prime, it's also a function of y. It just so happens that y double prime and y triple prime, the second and third derivatives, aren't on this side. But this is your function of x, y, and all of those derivatives up to the third derivative, potentially. In this example, this would be our f. So when you see this, even though it looks really abstract, think of this. This is what you'll be looking at. So you've got an nth order differential equation, and you want to solve for y as a function of x. Generally, when you do this, you're going to end up with a family of solutions. And since it's an nth order differential equation, I would expect to have n arbitrary constants in that family. So over here where I have a fourth order differential equation, I would expect the family of solutions that I get from this to have 4 arbitrary constants. We would usually call them C sub 1, C sub 2, C sub 3, and C sub 4. So that's the family of solutions, and maybe we're lucky, maybe it's the general solution, that family of solution that contains all solutions. Now, with an initial value problem, which consists of a differential equation and initial conditions, first you solve that nth order differential equation. So you find that family of solutions, hopefully the general solution with n arbitrary constants in it. And then you're going to be given initial conditions. If it's an nth order equation, you'll have n initial conditions. So you'll be given y at a particular x value. X naught will be given to you. They'll say when x equals x naught, y equals y naught. And when x equals x naught, y prime equals y sub 1. And when x equals x naught, y double prime equals y sub 2. And they'll give you conditions for y and all of y's derivatives, not up to the nth derivative, but up to the n-1th derivative. So here are n minus 1 numbers plus the 0th number there, that one with the y sub 0, that is the first number. So we've got a total of n initial conditions. And then together these two pieces make up an IVP. That's our initial value problem. So maybe we're given, to have a concrete example, maybe we're given this fourth derivative of y with respect to x is equal to this, and y of 1 equals 2, y prime of 1 equals -3, y double prime of 1 equals 0, and y triple prime of 1 equals 4. So that's a fourth order differential equation, and I've got 4 initial conditions. And notice also that y and y's derivatives that are given in the initial conditions, they're all evaluated at the same x value. That's true over here as well. If we were evaluating y or y's derivatives at more than one x value, that would be called a boundary value problem. That's something else, and you'll see that more in partial differential equations, not so much in this class. With an initial value problem, all of those values of the independent variable are the same. Now, if I look at this problem and I want to solve this problem, you might be tempted to try to take the antiderivative 4 times. And if you are tempted to try to take the antiderivative 4 times, I love that you're thinking that, because that tells me that you understand what this operator is. This says, take the derivative of y 4 times and you will get this, or you will get something that is equivalent to this. And so I think to myself, if I'm trying to find y as a function of x, and I have the fourth derivative of y with respect to x, in order to get y back, I think I should have to anti-differentiate 4 times, because I differentiated 4 times to get here, right? So that's a great thought. Unfortunately, it doesn't work, because this function on the right-hand side depends on dy dx. It also depends on y. Now, if this were a function of x alone, if I just had 2x cubed there, so the nth derivative, or the fourth derivative of y with respect to x, is just this function of x over here, then I could do that. I could solve that simple differential equation by anti-differentiating 4 times. And every time I anti-differentiate, I'll get a constant of integration. So it would make sense that I'd get 4 arbitrary constants in it, like I mentioned earlier. Because I had to anti-differentiate 4 times, now I've got these 4 constants. These conditions will allow me to find the values of the constants that will cause the solution curve to pass through the point x equals 1, y equals 2, with the slope of -3 at that point. And with a second derivative of 0 at that point, and a third derivative of 4 at that point. We would find that family of solutions, potentially the general solution, the solution that contains all possible solutions. And then using these conditions, we'd be able to find the constants. Now that's only if this is a function of x only on this side. If you've got y's and y primes and y double primes and y triple primes over here, we can often solve those, and we're going to spend most of our class solving problems like those. Or at least 1/3 of the content in differential equations is dedicated to solving higher order differential equations that look like that. But if this function is not a function of x alone, just integrating won't get us there, which is why we take a whole class in differential equations, and potentially many classes. This is just the first one. Okay, so this is your nth order differential equation. You've got the nth derivative as some general function of everything else, like this. And then you have n initial conditions. Let's solve a simple IVP now. This is not a simple IVP because of the dependence on y on the right-hand side. But simple IVPs these involve differential equations that can be solved with Calc 1 and Calc 2 methods only. So let's say you have y prime is equal to, let's say, sine of t times the square root of cosine of t. Now, from context, I see I've got a first derivative here, and it's equal to this function of t. So from context, I can see that y depends on t. And since this function on the right-hand side depends on the independent variable, that's t only, I can solve this using Calc 1 and Calc 2 methods. Now, that would just be solving a differential equation. If I want to solve an initial value problem, since it's a first-order differential equation, I would expect one initial condition. And let's say we have this. Y at 0 is equal to -2. And we want to solve this simple differential equation. That's the plan. I just want to show you again in abstract what this would look like. For a first order differential equation, you'll have y prime equals a function of the independent variable only. So f of x or f of t, often we use those variables. And then the initial condition would be y of x naught equals y naught. This number would be given to you and this number would be given to you. Now for a second order simple differential equation, we'd have the second derivative of y with respect to x is a function of x only. And of course, we could use different variables either for the dependent variable or the independent variable here. And then since it's second order, we'd be given two initial conditions, y of x naught equals y naught. So it's telling me the solution curve passes through the point x naught, y naught. And the slope of that solution curve at that point would be given by y1. So these are simple IVPs that you can solve using Calc 1 and Calc 2 methods. Now again, if a function on the right-hand side depends on more than just x, but y and y's derivatives, there are other methods for that, and that's what the rest of this course is about. So let's solve this simple IVP. I've got y here, and I see that it's a function of t. So the first thing I do when solving an IVP like this is I solve the corresponding differential equation. And when we solve the differential equation, if this is a function of t or a function of x on this side, you're just going to anti-differentiate. And we're anti-differentiating with respect to the independent variable, which is t. I'm using WRT as an abbreviation for with respect to. So y is, of course, the antiderivative of the derivative. Antiderivatives and derivatives undo each other. And I've got this over here. I think it will be helpful to write that square root as a 1/2 power, so I'm going to do that right now. Square root of cosine of t is the same as cosine of t to the 1/2. And then I go back to my Calc 1 and Calc 2 rules. I ask myself, do I have a rule for this antiderivative? And I don't have a rule in its current form because I've got a product of two functions. And whenever you have a product of two functions, you're probably thinking, or I would like you to think, I either have to use u-substitution or integration by parts. Most of the time that will work. Or potentially algebraic manipulation or some kind of trigonometric manipulation and then substitution using trig identities. But in this case, I think a u-substitution will work. Whenever I see parentheses, that's an indicator to me that I've got a function nested inside another function. So this function cosine of t is inside that square root function that we saw here, or inside that function raised to the 1/2 power. So I'm thinking u sub is probably going to work, so I'll let u equal cosine of t. Then to be sure it will work, I'll take the derivative of cosine of t with respect to t. Derivative of cosine is negative sine. Don't forget your angle, even though I didn't say it, negative sine of t, times dt, that's our du. These are differentials. And then I look up here and I compare what I have down here to what I have up here. I don't have a negative sign of t dt, I have a sine of t dt. So I'll multiply both sides by -1. And it turns out that sine of t dt is equal to -1 times du. So that's a negative du, and cosine of t is my u, so that's a u to the 1/2 power. So we substitute. Oops, I'm off the screen, sorry. We've got a u to the 1/2. Sine of t dt is a -1 times du. It's multiplying, so you can pull that -1 out front. And then I ask myself, do I have a rule for that? And I do, it's just a power rule. The antiderivative of something to the 1/2 power is 3/2 because I add 1 to the exponent. And I'll bring that negative down as well. And then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then we add c to that. And we're not finished until we have a function of t here. We're looking for y as a function of t. So we have to back substitute. So I have -2/3, and u is cosine of t, so we sub that back in. Raised to the 3/2 power plus c. That is our y. Okay, now if I was just asked to solve this differential equation, I would be done. We just had to anti-differentiate. We had to recall some Calc 1 and Calc 2 rules, u-substitution. So we chose u, we computed du, we wrote the integral in terms of u. Don't forget this step, a lot of students still do. Anti-differentiate. And then we back substituted. If someone asked me to solve the differential equation, I would be done. This is it. This is a family of solutions to that differential equation. We'll talk about whether or not this is the general solution when we talk about existence and uniqueness in another video. But we've got a family of solutions. Y of t is equal to this. Now we'd like to find the member of the family that will give us y of 0 is equal to -2. So when I plug in 0 here, the y value should be -2. So we're solving an IVP by first solving the differential equation and finding the family of solutions. And then the next thing we do is we use the initial condition to find a particular solution. I'm going to abbreviate that PS for particular solution. And this is how we do it. Like bringing back, what is that song from the 90s? This is how we do it. Okay, I'm dating myself. So we want y of 0 to equal -2. So we evaluate our function at 0. So you're going to substitute in 0, and then you figure out what that is. Cosine of 0 is 1. And then you simplify. So y of 0 is -2/3 times 1 to the 3/2, which is of course 1, plus c. In general, y of 0 is going to equal this. But we don't want this in general. We want a particular value of c that causes the solution curve to pass through this point. When x equals 0, y is supposed to be -2. So you substitute in t equals 0 here, and then you set this result equal to that y value. And then you solve for c. So c is -2 plus 2/3, or if you want, you can call that -6/3 plus 2/3, which is -4/3. And you're not finished yet. Your goal is to find a particular solution. So you evaluate y at 0, you set the result equal to -2, you solve for c, and then you substitute this value of c into this family of solutions that you found earlier. Okay, so we have y of t equals negative 2/3 times cosine of t raised to the 3/2 plus c, and c is negative 4/3. I guess I'll say minus 4/3. And that's my y of t. That's going to be well defined as long as cosine of t is positive. Ooh, that's actually a little bit tricky. So that's the solution. But remember what we talked about before. Whenever we talk about solutions to differential equations, we should also always talk about the intervals where this function is the solution to the differential equation. And y of t equals negative 2/3 times cosine to that power can be rewritten this way. That's the square root of cosine cubed t. Now this will only be well defined when cosine of t is positive or possibly 0. And we also need for this to be well defined when t equals 0, because that's what we're told here. When t equals 0, y is equal to negative 2. So our interval of existence for this solution needs to include the interval where t equals 0. So I look at my cosine graph. Now, this is not a graph of y of t, it's just a graph of cosine of t. I'm hesitant to even write y equals cosine of t. That y is not this y, clearly. But cosine of t looks like this. It repeats every 2 pi. And it's 0 here at negative pi over 2 and pi over 2, and then it's negative 1 at pi, and then it's back at 1 at 2 pi. We want the largest interval containing t equals 0, where cosine of t is positive, so that this is well defined. And I think that largest interval is this interval here. And I didn't actually trace out an interval, I traced out part of the curve. But this is the part of the curve where cosine of t is positive or possibly 0 at those endpoints. So the largest interval of existence for this function, where this function satisfies both the differential equation and the initial condition at the same time, is the interval negative pi over 2 to pi over 2. Now, I'm not going to do it in this video, but I do want to show you briefly how we would handle this if the differential equation were second order. So actually, I will do a very, very simple second order differential equation. So let's just start with y double prime equals 2t, y of 1 equals 3, y prime of 1 equals 0, and that's it. Because it's a second order equation, we get 2 initial conditions. Okay, now with this, I really just wanted to show you an example of y double prime. We're not actually practicing much integration here. If I'm trying to find y, well, first I need to get y prime from y double prime. The antiderivative of the second derivative would just give me y prime back. So we've got that. The antiderivative of 2t, we know we just use the power rule, bring the 2 down, add 1 to the exponent, divide by the new exponent, add your constant of integration. Now, since it was a second order equation, I will have 2 constants. So I'm going to call this first constant C1. The 2's reduce. So y prime is equal to t squared plus C1. I'm not trying to find y prime, I'm trying to find y that satisfies the second order differential equation and these 2 conditions. So if I'm trying to get y back and I have the derivative, I take the antiderivative again. Y is the antiderivative of y prime. It's the antiderivative of the derivative, gives you the function back. And y prime, again, is t squared plus c1 dt. That c1 is really important. Without it, you'll get the wrong answer. The antiderivative of t squared, we just add 1 to the exponent, divide by the new exponent. Dividing by 3 is the same as multiplying by 1/3. And the antiderivative of this constant is the constant times t. And then of course we get a constant of integration this time. So we'll call that C2. So this is a solution of the differential equation. If I was just given the differential equation by itself and I was asked to find y of t, that's all I would do. I would anti-differentiate twice and get this. And remember, the only reason why this works is because the right-hand side is very simple. It only depends on t. If it depends on t or just x, that's fine. If it depended on y or y prime, we'd have to do something else, which is what the rest of the course is about. So we solved the differential equation by anti-differentiating twice. And we got this family of solutions. It turns out this family of solutions is the general solution to this differential equation. So I'm going to label it that way, the general solution. Now we want to find the values of C1 and C2 that cause our function to pass through this point. When t equals 1, y is supposed to be 3. And when t equals 1, the derivative of y is supposed to be 0. Those two conditions are going to give us two equations and two unknowns relating, well, C1 and C2, maybe possibly to each other or to other functions. So first I'll use this initial condition. I replace t with 1. And so what I get is 1/3 plus C1 plus C2, and that is y of 1. And that tells me that y of 1 has to be 3. So I'm going to set those equal to each other. This gives me one equation with two unknowns, which doesn't help us very much. But I also have this second condition. It's saying y prime of 1 equals 0. So in order to find y prime of 1, typically we would differentiate the result. Actually, we already have up here that y prime equals t squared plus c1. So I've got my input squared plus c1 is y prime. And then I want to input t equals 1. So I get 1 plus c1. And that has to be equal to 0. So we replace t with 1. We set y prime equal to 0. And since this is one equation with one unknown, you can solve for C1. So we have 1/3 plus C1 plus C2 equals 3, and 1 plus C1 equals 0. Solving this for C1, we get C1 equals -1. And if C1 equals -1, we'll have 1/3 minus 1, which is -2/3, plus C2 equals 3. And then we can take this equation and solve it for C2. C2 is 3 plus 2/3, or 9/3 plus 2/3, which is just 11/3. Okay, so we have C1 and C2. Again, we're not finished until we substitute those back into the general solution or back into that family of solutions that we found earlier. So we have y of t equals 1/3 t cubed plus c1 times t, and c1 is actually -1, so I will just say minus t. -1 times t is -t, plus c2, and c2 happens to be 11/3. So that is the solution to the differential equation that passes through the point x or t equals 1, y equals 3, and has a slope of 0. Now, if you're not sure, if you want to check, you should take the second derivative of this and see if you get 2t. So let's check our work. We have y equals 1/3 t cubed minus t plus 11/3. Y prime, well, it's 1/3 times the derivative of t cubed, which is 3t squared. Bring the power down, multiply by t to the 1 less power. And the derivative of a constant times t is just the constant. And the derivative of the constant is 0. So we get y prime is t squared minus 1. And y double prime, The derivative of t squared, which is 2t, and the derivative of -1 is 0. So y double prime equals 2t. That's good. Checks out. The differential equation is satisfied. And y of 1 is supposed to be 3, and y prime of 1 is supposed to be 0. So let's check that. Y of 1 is 1/3 times 1 cubed minus 1 plus 11/3. So I have 1/3 minus 1 plus 11/3. 1/3 plus 11/3 is 12/3 or 4. So you get y prime of 1, or excuse me, y of 1 equals 3. That's good. And y prime of 1, well, remember y prime is t squared minus 1. So we're going to have 1 squared minus 1. And 1 minus 1 is, of course, 0. So that second initial condition is satisfied. So that's how you solve a simple second order IVP. Remember, if the differential equations look like this or this, you can solve them using Calc 1 and Calc 2 methods. So you might be using basic antiderivative rules, u-substitution, integration by parts, possibly partial fraction decomposition, and that's pretty much it for this course. As long as you can do your basic antiderivative rules, u-sub, integration by parts, and partial fractions, you'll be able to evaluate the integrals in the course. Now, for the rest of the course, the differential equation will tend to look like this. So you won't just have a function of the independent variable on this side. You'll have a function of the independent variable and the dependent variable and the dependent variable's other derivatives. It's going to be much more involved. Solving those types of differential equations is what the rest of this course is about. So that's it for IVPs.